I turn it over to our distinguished lecturer, I just want to talk a little bit about this seminar series that we're in the process of putting together. So in addition to this being an ISR distinguished lecture, this is also the kickoff seminar for the Microsystems seminar series. So I think you're going to see a pretty prestigious lineup that we're putting together. We're almost completely filled out. So we're going to start with Professor Howe in October. We have Joel Burdick from Caltech, who is one of the robotics guys in the world. So we'll actually make that a co-seminar with the Robotics Center. That should be excellent and highly entertaining. In November, we have Svetlana Tatish-Lucic from Lehigh, another great young MEMS faculty. In December, we're excited to have Jack Judy from, I guess he'll still be at DARPA. We think he'll still be at DARPA at the time, but from UCLA, more formally. Then we'll take off for December, January. In February, we'll have another MEMS guy, Tahir Saeed from the University of Illinois. In March, one that I'm very excited about, we're going to have Mehmet Toner, who's one of the hot new microfluidics kings these days. And then April and May, I can promise you we're going to have some pretty big names, but I'm not going to tell you who they are yet. So with that said, like I said, very exciting year. Once a month we're going to have some really high-impact speakers coming through here. It should be a lot of fun. And to kick off, we have a super high-impact speaker here visiting us. We've had a great time with him today, showing off the MEMS work, the Microsystems work that we're trying to put together here. So Professor Roger Howe is a professor at the Stanford University Department of Electrical Engineering. Heard some good things about that. That's a good place to be, I've heard. So Professor Howe got his BS in physics, actually, from Harvey Mudd, and immediately went into faculty from there. Was faculty at Carnegie Mellon. I did take it. Yeah, sorry. There was a PhD in there as well. Yeah, so PhD from Carnegie Mellon. Oh, sorry, from Berkeley. I'm jumping ahead here. PhD from Berkeley, then became faculty at Carnegie Mellon. Then became faculty at MIT, and then came back to Berkeley. So spent a number of years at Berkeley until 2005, switching over to the other side of the Bay, and has been at Stanford since then. While at Stanford, he has been the faculty director of the Stanford Nanofabrication facility, and very, very recently has become the principal investigator of the National Nanotech Infrastructure Network. Along the way, in 1996, he was elected IEEE Fellow, and of course, a big badge in 2005, elected to the National Academy of Engineering. So we're very lucky to have a member of the Academy here to deliver this seminar. Thanks so much for coming out, and we look forward to hearing it. Thanks, Ian.
So appreciate your coming to this seminar. Our first day of classes is Monday, so we're at a quarter school, and this is a little bit of a warm-up for the hordes of people. I'm speaking to the newly admitted grad students tomorrow morning, actually, back at Stanford on research in the physical side of EE. So this topic, well, this is Microsystems, is something that would be very much rooted in your ISR activity as one of the important emerging applications of systems. But I think it's not normal that we would think of that in the context of energy conversion. I'll mention one significant other application of a system in which vacuum is not just the encapsulation, but very much intimately involved in the operation of the device. And so I think before we get into the devices, I would like to spend some time reviewing the history and current state of various ways of encapsulating MEMS devices in vacuum. In the vacuum packages, some people go back to the metal can packages that were pioneered in the 1960s, and that would be a serial packaging at the die level. In MEMS, there's been a big push to do things at the wafer level. That leads to lower cost, and in some cases leads to much better control of the vacuum. Lately at Stanford in the last year, we've been working on sealing up packages at the wafer level without depositing a film, which would be a new direction based on some work partly in my group, partly in Tom Kenny's group. The application of this vacuum capability, now we can look at applications that demand a very high quality vacuum in a harsh environment, and the cost of that wafer level packaging is like many things in an 8-inch or even 12-inch setting. This is something that begins to become a very minor speed bump in fabricating the device. So this thermionic energy conversion is hardly new. In fact, it goes way back into the previous century. I think several new twists. I'll mention one that's published that would come out of a group in material science where we are doing a different type of thermionic conversion. That was a Nature Materials paper in 2010, photon enhancement of a thermionic converter. And Tom Lee and I, Tom has left Stanford on leave to run the MTO, Microsystems Technology Office at DARPA. But before he left, we have this collaboration in micro vacuum terahertz sources. And again, in vacuum, you have a very long electron beam-free path. You can do things with electrons that are not possible in solid state. And so, for just reference, Tom Lee is someone who's never worked in exotic electron devices. His career was built on a book called RF CMOS. Building radios out of our digital technology. When he first gave his presentations, people laughed in the early 90s because CMOS was so pathetic as a radio substrate. But then he launched some companies, and these companies became multi-billion-dollar companies, and eventually people stopped laughing, and all the radios in your cell phones would be CMOS radios, all derived from Tom Lee. For him to abandon that and go vacuum is a truly shocking thing, and I'll try to pull together some conclusions. So, without a long introduction, some of you, how many of you are in MEMS classes this quarter, or semester, I should say? Is there a MEMS class?
Not this semester.
Not this semester, okay. So actually, we moved ours. Normally it would be in the autumn quarter, but we moved it to the spring to better coordinate with the various departments because we're drawing across the School of Engineering and beyond. But this would be a topic in a MEMS class, this wafer level kind of processes. And they would go back even before the 1980s. There was the invention of a silicon glass anodic bonding process that would be something that so old school students are reluctant to do it, but it's a very reliable process that leads to a vacuum seal between certain kinds of glass and silicon or metals. In the late 80s, I'll show some of this work at Yokogawa. This was a really disruptive event that people were sealing a micro-machine structure with a deposition. This was an epitaxial silicon growth. It was sealing up microcavities, so the devices were in a vacuum shell, each device on the wafer in a vacuum shell. There was an NSF visit to Japan, and they saw this work, and it had a huge impact on the US in terms of modifying research priorities, even some of mine. I was a participant in these various other sealing processes through the 90s. In the 2000s, there would be a work at Stanford in Tom Kenny's group on using epitaxial silicon depositions. The big contribution would be getting electrical interconnects through the vacuum. And finally, recently, we're working on doing the sealing in epitaxial layers or single crystal silicon layers with no deposition at all, which is kind of interesting. So let's look at some of these old SEMs. This would be Ikeda's work in 1988. You see the tine, like a fork tine, but this is a double-ended tuning fork resonator built into a pressure sensor that they published in 1988 and are still producing. It's a precision pressure sensor because the frequency of that resonator shifts under deflection of the membrane. And so this is used in industrial control processes. The Q is very high because this is vacuum in here. This has been cracked through. This was built with etch access holes to micro-machine out all of the oxide, and then they deposited this epi layer and seal up all the holes. Hydrogen was sealed up with it because in an epi reactor, if you use that, there's basically a hurricane of hydrogen going through to create the right conditions for epitaxial silicon growth. How do you get the hydrogen out? You heat it up in a nitrogen furnace, which you have in your nano center, and the hydrogen goes out and the nitrogen can't get through, and you end up pumping a vacuum and having a very tightly controlled environment. Later on in the 90s, some of you may know Leeway Lin. This is the L-Lin on one of the et als with Alto. This is a comb drive structure that's actually beginning to move around in the SEM. You can see the imprint on this thin film layer cake that's built up. If you look in the patent literature, you'll find all kinds of interesting twists on this, of ways of depositing films to seal up things underneath, opening etch access holes, etching out the sacrificial layer and sealing it up. It would be in various stages of commercial production. This is silicon nitride spanning this large area. One problem is our MEMS are not necessarily so easily packaged as having this very narrow beam that you can span. Here you have mechanical issues of atmospheric pressure across that, and of course if you're going to put it in a plastic package, that's even more challenging. So along those lines, giving this tour, here's a classic gyro, classic in the sense that it's a turn-of-the-century gyro. Ashwin Seshi is a former student of mine who's at Cambridge University, would still be working on inertial sensing. This is designed in a foundry. One of the things that was possible for the older generation of students in the late 90s, Don DeVoe being one of them, Professor DeVoe, excuse me, would be that there were ways of getting MEMS fabricated in these foundries. And so the students were designing the electronics, and some of the mechanical engineers were designing very good electronics, and electrical engineers designing very good MEMS, and the mass sets would go to San Diego and we get the wafers back. And we could get the chips back, and just like a CMOS foundry, we could test things and get some cool publications. This is a very complicated resonant output gyro, but how do you vacuum package this? And there was a group at BSAC at the time at Berkeley, and John Heck, now at Intel, would have led that with Professor Sujay King, now Sujay King Liu. And the idea was to build a microcap on a donor wafer and bond that on just the gyro and leave the electronics unvacuum packaged. They didn't really need the vacuum. And you could do a gold silicon eutectic. There were various other ways of doing eutectic. This is a silicon germanium lid, and we could span millimeters by this molded microstructure. So this is built in a waffle grid, and thin films are deposited and then released, and we have our microcap. This is, again, turn-of-the-century technology. In production, it turns out that's not the case. Here is an example of production from a company that acquired a company that I co-founded. Okay, so I've only co-founded one company in my entire career, and that would be Silicon Clocks. You've heard of Silicon Time? Silicon Time is a Stanford spinoff. Silicon Clocks is a Berkeley spinoff. That would, there's a long history of naming at the same time, roughly, and coming up with these similar names. But Silicon Labs wasn't a MEMS company. Emmanuel Kevy was a former postdoc in my group. And so you would have CMOS, and then MEMS built on top of the CMOS. And then what's bonded on is a complex pre-processed wafer that ends up with a single crystal silicon cap bonded on each MEMS chip. And there might be 40,000 MEMS chips on this wafer with MEMS stacked on CMOS, and you end up with these little vacuum shells. The junk in here is from the SEM sample preparation. You have this nice vacuum cavity. So if you want 10 million of these, you can order those, and there are people who know how to do every step of this and put this in plastic. It's nice to have that packaging side of MEMS more or less under control. So is this good enough? Well, the vacuum control in here is not hypercritical. This particular resonator is at a frequency where the vacuum doesn't have to be all that great. It won't affect its performance particularly. With that introduction, moving to Stanford, this is where Rob Candler, some of you may have met. He's a electrical engineering professor at UCLA. He was an EE student of Tom Kenny, who's a mechanical engineering professor at Stanford, though he's never taken a course in mechanical engineering, which would perhaps be a prereq for being an ME prof now. He was a Berkeley physics PhD from an experimental group, and And when I met him, I was over at his house at this party, and he was wanting advice from me on microprocessor interrupts in some kind of real-time control class he was teaching. He didn't know that much electronics. He thought I might know some electronics. I'm just kind of an analog guy, and I've never dealt with that. So he's learning essentially digital electronic hands-on stuff to teach MEs. Our best practical electronics classes at Stanford are often in the ME robotics and systems area. So in any event, Rob got excellent training from Tom and built these double-ended tuning fork resonators. The resonators are not the focus initially. The initial focus is how do you vacuum package them. This is a stack of thin films that are packaged that have vertical feed-throughs. So it's not just a single conductor on top. You can get interconnects to those. And so this was disruptive. It allowed you to build tiny resonators with vacuum packaging, and this would have led to the company Silicon Time, which is still going independently. What are some of the problems? Let me go, all of a sudden, I'm going the wrong way. Okay, wait a minute. Okay. So the way this is done is that you have remote from here holes in this membrane. You remove all of the sacrificial layer, and so you have a microstructure in there, and you deposit epi. Now, some of that epi gets inside. There is, it ends up being somewhat like the Yokogawa process. You have hydrogen, you have to drive that out. But the fact that you can now make local interconnects, you can bond this, you can flip chip it on CMOS and make a integrated clock. So the SEM cross-section shows the very tight cavity. It's this form-fitting cavity around the device. It can't move very much. That's because of the way this thing was made and the need to planarize the surface with this upper sacrificial layer. If you have canyons here that are too wide, you can't fill the gaps with a thin film. So there's technical details that make this a very powerful packaging technology, but very, very limited. Most MEMS you want to move. Imagine if you wanted to make something like a fatigue test structure, you would have to have enough clearance to move a large distance. So in fact, this shows a cross-section of the interconnect to the electrode layer. So this is Bongsang Kim. Bongsang is at Sandia National Labs, and Renata Melamud is at Silicon Time, Rob and Tom Kenny. So the one attractive thing, and so this is about the time I show up at Stanford. I remember meeting Bongsang, and he was testing these resonators. This is a double-ended tuning fork that's anchored in a funny way. It's anchored in the center, and it's actually driven in a way that would decouple it from the substrate. A lot of interesting resonator designs to make stable references. And this has a respectable quality factor at 155 kilohertz of 30,000. It has a significant, and there's a negative sign here missing, temperature coefficient that was later worked on, and it has an incredibly boring kind of response. You know, imagine the grad student, it's 8,000 hours, and you're saying nothing's happening, right? This is exactly what we want in a clock, to have this kind of thing that's dead stable. So the vacuum is an incredibly stable, boring environment. It's like a tombstone kind of place, and so this actually stimulated discussions with Tom and Olaf Solgaard. Could we extend this into something more general, where you could do general MEMS underneath this kind of cap with the same performance? And two students, Andrew Graham and Matt Masana, dove in and did a couple of ends of this. In their last one, they merged their efforts, and actually this is kind of a schematic of a fatigue structure or an inertial sensor or something. With these isolated interconnects, they're like little coax interconnects through the structure. You have all of these vent holes and the structure underneath. How did we get this green layer? We actually did wafer bonding and transferred single crystal silicon. So we didn't do all thin films. We bonded and did a donation of a layer, and then we didn't, but the bond was not the vacuum seal. We opened it up after bonding and then sealed it using the classic same line. So we call it a hybrid or a two-step approach. After you open it up, you go through the epi-seal, seal it up again, punch your feed-throughs, and make your integrated MEMS. So Shingo Yanioka was a PhD student. I signed his PhD, it seems like 3 weeks ago. We have a summer filing for PhDs at the end of August, and he made it and went to MCube. I don't know if you've heard of MCube. That's a startup doing inertial sensors in Silicon Valley. Let's see, Matt Masana is at Skybox, some kind of a, go on the web and see what they do. As I understand it, if you want a picture of your house or something, they can arrange for a satellite to take a picture of it, or maybe your neighbor's house or something. I don't know what this thing is, privacy concerns, but in any event, he went that route. Andrew Graham, straight and narrow, the Bosch MEMS group. So we would have these people sort of, but some people might be interested in what's happening to our students. They aren't going to academic media, they're going into the industry. So anyway, we can do a fatigue test structure. He didn't design it aggressively enough, so we were unable to break it. We were unable to see fatigue, even with this large clearance, and there's a stress concentrator in one of these fan-shaped resonators. We were unable to see fatigue anyway, but at least we could do that. So lastly, I'm going to show work that is 3 beams in 2010. Hyuk Chu is a Berkeley guy who was became a postdoc at Lawrence Berkeley Lab. He just moved to Caltech as a faculty member. He's that guy. Rishi Kant is my PhD student, and he worked with Hyuk on this, seeing if he could extend the silicon migration phenomenon that people call hydrogen annealing. Those that are into silicon technology would know that you have extreme mobility of surface atoms on silicon, well below the melting point. Melting point's 1412. At 1100, you see things like these holes flow and seal. Okay, you're not melting it. It's this a surface migration phenomenon. And Rishi, being a part computer scientist, wrote the code, which was no mean feat because of these bifurcations, to predict if you had a cylindrical hole, when you annealed it for 1100 degrees for 40 minutes, what would you get? He predicted void and he predicted volume contraction because of mass conservation. And lo and behold, you see the volume contraction. You can see the ghost-like appearance of those voids in there. So in any case, to apply this to MEMS packaging, we don't have deposition anymore. Okay, we just heat it up and you seal your membrane. We could do it in hydrogen. We can also do it in any low-pressure reducing environment, including ultra-high vacuum. So here's was Andrew's final push last summer, was to see if he could build MEMS using the two-step approach without a deposition. And he sealed it, but due to the volume contraction, you don't have enough rigidity to hold up under an atmosphere, so he deposited more epi. And if you notice some interesting features, the cone fingers are rounded because there was migration on the structural layer itself. This could be beneficial for putting fillets into structures and healing the kind of etch artifacts. And we were able to again build fatigue structures. The yield was, Tom Kenny's got his students, he always has them do a lot more testing than would be the case often in my group. And so he was getting significant yield on structures in this new kind of sealing. So the takeaway then is at 1100 degrees for 40 minutes, you can seal things up. A lot of our devices don't appreciate 1100 degrees for 40 minutes. So a long-standing collaborator, Sharif Sekhi was on sabbatical at Berkeley in 2002 and 3, and he's visited me at Stanford. He's a professor at American University in Cairo. We have an IEEE MEMS 2011 paper where the same process is done with a local laser annealing. So he has a pulse laser that heats just the surface, and his student emailed me last month, is trying to model this. This is more like melting, but at the bottom it's cool. So it's a surface like the ultimate rapid thermal kind of annealing, and we can seal up the surface and keep the substrate cool. So in fact, to apply this for packaging could be very interesting. This should be an S here. I keep forgetting this type of 24 nanosecond pulses, 2,000 pulses at 1 hertz, significant energy flux, and you're able to actually transform the surface of silicon. So this is a process done in his laser, which he's worked on for a number of years. So In any event, I think vacuum at the wafer level, not the one-off handcrafted package level, reproducible vacuum is something that we can count on in MEMS. So now that we have vacuum, maybe we can charge into applications that need vacuum. Let me start with thermionic energy converters. First of all, here's a problem. It's almost like threshold voltage and thermal voltage in teaching semiconductor physics. There's all THER is common, right? We have too many common letters. This looks a lot like thermoelectric, right? In fact, but it's not. This is something that predates that. If you heat a cathode or an electron emitter very hot, you end up having electrons come off, thermionic emission. People might remember these cathode ray tubes that predated flat panels from the previous century. They had electron guns in them, right? Electrons came out and they were steered in place. It's retro technology. Anyway, so you can do that by just heating it up. And vacuum tubes, if you're into retro electronics, have little heaters and things. So in fact, the electrons come out. If you have a cool or relatively cool collector or anode, you end up having a current. You can pull energy out of this, electrical energy, and you can reject heat at a relatively high temperature. The concept, 1915, Göttingen University in Germany. Demonstration in the Soviet Union. Look at these dates. You wonder if any of these guys survived the world wars that were on or happening. And an American guy, Hermvist, at RCA in '57, demonstrated a converter with 5% efficiency. There was a huge investment for a period of about 30 years, and the application was space, that you could have something that would directly heat to electricity, and that could be suitable for powering deep space probes. Where would you get the heat? Well, we'll look at that in a minute. But if you look at thermionics, it goes back a ways. Thomas Edison, an American inventor, was looking at the problem of soot in his early light bulbs and the degradation of the filament. He had something in there, and he noticed he was getting current out of the filament. And so he called them thermions, and that actually immediately developed a diode patent, and so he was a very inventive guy with 1,000 patents. No Nobel Prize for him, but J.J. Thomson was doing cathode ray tubes a century ago, or more than a century ago, and names the electron. Fleming was contributing vacuum tubes and diodes, and then Richardson, in his famous, now called the Richardson-Dushman equation, was modeling this, where you have this exponential dependence on what is the cathode work function. The A coefficient is neglected. That coefficient also has to be large in order for this to work. So here we are in the 21st century. Why are we revisiting? Wasn't this all done? Well, let's continue, keep that in the back of your mind. Why would this be interesting? So Igor Bargatin, borrowing some slides, is a postdoc and now research associate in my group, my first pure physics PhD, who is now becoming someone who's much more on the micro systems end of things. This is the energy band diagram with a couple of metals. So you have to get this tremendous heat to get this tail, have enough energy to get out and get out of the metal, get out of past the work function and get collected by the anode. So what are some of the problems? Well, you can see heating and stability is an issue, and you can work on that by getting working on both work functions, but you need a difference in work functions. Okay, you want them both low. It'd be nice if the anode was extremely low, and but on the other hand, you need a difference, because that's basically going to be your output voltage. You have radiated heat transfer between the cathode and anode, so you have kind of a thermal short. And you also have to make interconnects on this thing, and you're going to have thermal problems there and conduction issues. So do they work? Well, here's one being unloaded from a military transport plane. This is a Soviet product. The Topaz 2 reactor was launched in 1987 in a spy satellite. the end of the Cold War, it was flying over the U.S. And taking pictures with this thing, this roughly 5 to 10 kilowatt, powered by a nuclear decay or nuclear pile, and that raised some issues to have this tremendous amount of radioactivity inside this thing. It's also hard to get the heat. Where do you radiate the heat? So it's a major technical challenge to make something rugged enough to launch into orbit, to ride up the boost phase. Is not a trivial thing. And so how did they make it? With vacuum tube technology, precision machining, pushed to the limit, 100 micron gaps between cathode and anode, controlling temperature. They worked on this, and it was basically mid-60s technology that they froze and flew in the 80s. In the US NASA efforts, they kept having ever better cathodes and anodes, ever better laboratory demonstrations. They never flew it though. They kept working on it. So you have the different technical cultures. This thing does look like something. So this is Kirtland Air Force Base in Albuquerque, New Mexico. The location is, and I don't have a date on this or whether this was, having lived through the Cold War, to have something from the Soviet Union appear in Kirtland, it was studied very carefully. I've heard rumors they dropped this thing off the back of the truck, and it didn't work after that. But anyway, so but we didn't. But how much did that cost? The Russians had funny accounting. It's just unbelievably expensive, billions of dollars, and I'm sure we got it on about a tenth of a penny per ruble or whatever in the end of the Cold War. So in any event, that stimulated some work in Sandia National Labs, which is attached to Kirtland Air Force Base. I don't know if Don King, who actually had a lot of ties with Sandia, he's not a MEMS guy there. He thought this is right out of his patent. Wafer bonding, doing microfabrication, getting the spacing to 1 micron, which many people in the room are building features on that dimension. Gaps are things that MEMS people know how to do. He has idealized thermionic emission current densities, realistic work functions. He's arguing he can get to 30%. Why the extra efficiency? The large gap in the Soviet design, they had to put a plasma in there to avoid space charge limit effects from the cathode to the anode. So in fact, by scaling to 1 micron, you change the physics and you get around that limitation. So in any case, this is a patent, and the provisional filing date is only to a few years after that. So I'm showing you that people have been interested at some level. Oh, another interesting thing, the lead guy, Boris Moises, of the Soviet thermionics program, retired to Stanford after the end of the Cold War, and had a courtesy appointment in applied physics. A guy named Ted Jabal, who has a lab named after him at Stanford, famous superconductivity. He and Boris hung out together. Boris passed away a couple of years ago, but he spent 10 years at Stanford. They wrote a paper together you can find in the Journal of Physics D that's directed at all the people in the room. We basically should quit wasting our time doing applications and go into thermionics because it's going to save the planet, that kind of thing. 2 old guys from the 20th century. So I actually read that paper and thought about it a lot, and that helps stimulate this project. So in any event, I didn't realize Boris was the same guy. Took a little bit of Russian, but he's running a conference in Moscow in 1973, and then he's surfacing in the 90s at Stanford. So anyway, Khalil Najafi needs no introduction. He's one of the leading MEMS guys on the planet. And his student Chumbo Zhang, who I ran into at Ken Wise's retirement celebration, hadn't met him before. This is the conference at Transducers 03 that I was the technical chair of, so I should have met him, but I was too busy, overwhelmed with the running the conference. This is a combustion micro thermionic converter, so you burn something to get the heat, and then you turn the heat into electricity. This is sort of a microwatt kind of thing at the initial demonstration. They're using barium oxide on tungsten for producing work function. So a heroic thing for a grad student to do at the University of Michigan. So what have we been up to at Stanford? Well, I'm going to go through this in several layers. If you look at the physics of this, some of you may be aware of a device called a bolometer. Bolometer is something that measures infrared flux. They make cameras that way. It's very much a thermally isolated structure. So we're borrowing the kind of folded suspensions that people make in a bolometer pixel, but this is a bolometer on steroids because we're going to heat this thing to 1,000-degree plus. And so we thermally isolate from the substrate. This is silicon carbide. This is N-type polysilicon carbide from a tube in the Berkeley lab. And Roy Mabudian's group collaborating. Interesting things happen with work functions. It's very much a surface phenomenon. Silicon carbide has work function of 4.5, but in operation, this device shows a work function of 3.4, which is much closer to what you get in a graphite. And so the surface may be actually transforming.
So what's the thickness of the silicon carbide?
The typical 1.8 micron, something like that is a typical MEMS layer. Very much like polysilicon. So what we have done is a very simple, like one mass surface micromachining. We use xenon difluoride, we use vapor HF and things that are just to demonstrate the cathode. Where's the anode? We have an integrated package. So back in this early era, if you look at the efficiency as a function of various work functions and the cathode temperature, there's a huge incentive. Remember, we were at 3 point something EV, way out of what would be reasonable. But if you get down into these lower work functions for the cathode, and of course the anode has to be even lower, you can get very impressive efficiencies that would become quite interesting. There's work, Nemenich's group at Arizona State has published papers with nanocrystalline diamond where they have work functions of 0.9 eV. And that would be a new material. So again, why revisit this? Didn't they work on it in the 70s and 80s? Well, a few things have changed since a few of you remember, the 70s and 80s. The ability to control surfaces, interfaces, nanostructuring ability, capabilities, depositions of polycrystalline or nanocrystalline diamond or polysilicon carbide didn't exist in those days. It's a whole new material set and technology. So in fact, 0.9 is off scale here. Maybe we're going to use that for the anode. There's issues with diamond. A diamond is not very well understood. Talking to the diamond guys, they are the coefficient A in the Richardson-Dushman coefficient is so non-uniform over the surface, and the bright spots are unbelievably bright. If the whole surface was bright, it would be the material, and they don't understand the physics of why it's got these bright spots, having their whole groups working on it. So I have a new project that Igor helped nucleate, and a student, Sharon Chow, who's working on it. We have a new professor, Jens Norskov, from Denmark, who is a computational science guy in chemical engineering. And so what we're trying to do is use things like density functional theory to model new materials and predict the work function. And what are we going to use to synthesize those? The platform is atomic layer deposition. It's something where we can get near monolayer coatings that could be very interesting. So the benchmark is cesium. Cesiated tungsten is what's known and very well studied. And this is a prediction of in fact, the coverage and this is about a 3/4 monolayer coverage, and the effect on work function. You can see it's dramatic on tungsten, and it gets down to around 1.3 eV or something like that. Cesium is not an easy element to deal with, and we would love to dispense with it and work on another approach. The Richardson-Dushman coefficient is a much more fundamentally interesting problem to Norskov, who's a computational guy, because you're trying to ab initio calculate the ability for electrons to get out. It's not enough to have a low work function. You have to have tunnels through to get out. So it's my first bumping into something where my student Sharon would be loading a major cluster at SLAC with her computations. I've never had the satisfaction of knowing one of my students is just burning computing power before, and it feels good actually to know that those massive arrays of computers are doing something useful. For me, it's a new experience. Normally, my students go into the fab and Nano Center, and they work hard in there. But she is someone who I'm going to send her in a bunny suit for cultural enrichment. But she is very much tilted to the theory side. So In any case, you might say cesium, if you go on the web, you find some interesting videos of people with cesium, and it's a material that you don't want to have exposed to air in large quantities. There have been a lot of people interested in cesium. This is work at NIST. Lou, a few years ago, big push on the chip-scale atomic clock program, which NIST would be a leading institution pushing, and I don't know if there was a Maryland project, but there certainly was one at Berkeley, Alto, working on sealing up and making a little physics package for an atomic clock. And what is the key material? Cesium. So they're bonding it in a wafer bonding case we can handle cesium. So we have to go there, which I hope we don't, because I think there are new materials that would be better. So thermal isolation is something that is a fundamental issue. So we're just joule heating this by passing current through it. I'll later show some optical heating. Things are getting hot and hotter and even hotter. Okay, so we're able to, with our pyrometer, estimate this as around 2000 C. You know, silicon carbide is a thermally robust material. It's not a good electrode material, but it's a material we've got our hands on, and we would be, it's clearly something that could be very nice for suspensions. So I didn't put this in my plenary talk because it's a little bit provocative, but there was a committee that was convened by the US government, this organization called Dept, and they looked at this advanced thermionics program. I forgot the date is 2001, and they looked at the potential of the micro-thermionic converter that had been proposed by Don King. And I should have highlighted this, there's a lot of text here, but he says basically 500 degrees separated by a micron, you MEs would look at a 5 times 10 to the 5th Kelvin per millimeter kind of thermal gradient in the connecting structure, and I got problems with parasitic heat, and basically sustaining such an enormous gradient with tolerable thermal conduction losses is not credible. And as a result of some things like this, they basically ramped down funding 10 years ago on that effort. I think there's certainly thermal challenges, but in fact, I think we have materials and designs that would be able to meet that challenge, partly derived from all of the hard work the MEMS, the MEMS industry, I guess a lot of electronics, if your accelerometer only had to work at room temperature, it'd be an easy design. To have clocks, accelerometers, and gyros that work in Siberia and Death Valley, California's furnace east of LA, where the record temperatures would be in the 130 range Fahrenheit. That is a major thermal engineering challenge. Well, we're going to have big thermal engineering challenges here, where the structure has to be stable. So in fact, in electrical engineering, the thing that's going to fail is always the interconnects are the problem. You have issues with interconnects. And I ran into some people from France who were working, we were actually on their way to a DARPA workshop that are big on electronics and MEMS at extremely high temperatures for instrumenting gas engines, putting things into the hot zone. And this is a indium aluminum nitride high electron mobility transistor for you EEs in the audience, operating for a couple of hours at 800 degrees centigrade, where I've often pushed wafers in at 800 degrees centigrade. This thing's operating at 800 degrees, and they've worked on this tantalum copper interconnect, and it doesn't appear any worse for wear, okay, on this, for being roasted like that. And this is in the range of the kind of operating temperatures we're going to get to. Of course, we may have high current densities, and we have to have low resistance interconnects, but it's not something out of the question. And in fact, in my longtime collaborator, Roya Mabounian, and her student, Feng Liu, ended up at Analog, okay, was up at designing MEMS up in Boston area. But they worked on this is Applied Physics Letters last year. This is the typical silicon carbide platinum contact running in air up to 500 degrees, and it's getting more resistive the hotter it gets. And I forget how long this is running at 540. But then this red curve is their nanographitic carbon interface, which again, nanostructured material that appears not to care at all. The furnace only goes to 540, but this is not in vacuum, this is in air. Okay, so I guess the takeaway would be our interconnects can go to these very high, harsh temperatures, and I think that'll open up a lot more applications than thermionics. Let me just run through the research prospects. I think there's a tremendous amount of promise if you think of graphene, nanocrystalline diamond, and ALD-based coatings. We can engineer those surfaces to a degree that was inconceivable. What we're doing now is the micro platform for it. Ultimately, the emitters might be nanostructured. They might have interesting new materials. And there's a tremendous amount of research to get the components right. We haven't even addressed surface area. We have to work on the interconnects. It's a wafer stack. We have to get the feed-throughs, all of these practical issues. Thermal expansion, I'm confident your class in MEMS can deal with, and your mechanical engineering genius approaches to overcoming that. Vacuum encapsulation, I think, will be not a problem. And the high temperature electronics might be nice at a wafer scale thermionic converter to do some signal or power conditioning in the midst of that. So I think there's a lot to do, okay? There's no question, and as an academic exercise, I think will be exciting. But in fact, one of my early conversations on this with this guy, Nick Malash, Nick is a Santa Barbara PhD in chemistry, who is a material science prof at Stanford. And in March 2008, he's a diamond guy, so I was talking about diamond. And he said, you know, forget diamond, no one understands it. So, okay, thanks, Nick. But he went home that night, and being slightly younger than I am, didn't sleep much that night because he got to thinking, why not get rid of the metal and go to a semiconductor photocathode? And no one had thought of this. A lot of work in semiconductor photocathodes, often cold, you know, for imaging and other applications. This is a hot photocathode, and he cooked up this idea, and basically it took a long time, 2 years to demonstrate it. Jared Schweid is Nick's student, Igor pitching in. So this is a twist on this that makes a huge impact, and I'll show you in the band diagram why this is important. We have, for those that have seen these band diagrams, a semiconductor now. We have a band gap, and so we have a quantum boost if you're at the right wavelength to get enough energy over there, over the band gap, and not enough to emit direct from the valence band out. You end up in the conduction band where you thermalize, but you have an easier hop over the electron affinity than you do over, you know, off the work function. So you have a lower barrier. It's kind of a two-step process, and so you use the optical energy and the thermal energy. Thermal energy is not lost. The device wants to be hot, unlike a photovoltaic cell, and so you basically are recycling this heat. The anode is still a metal. Igor has some great ideas on actually looking at that as a different material as well. So my grad student Jay Lee, and this is transducers in Beijing, we have a single crystal silicon carbide from Cree. We do a smart cut process, hydrogen embrittlement, make a wafer with spin-on glass and oxide, flip it over, bond it, and transfer a micron or two of silicon carbide and fabricate one of these structures. We need the crystalline silicon carbide, the P-type silicon carbide, to see this photon enhancement as easily as possible. And lo and behold, we have some experiments. This is a log scale. Obviously, the currents are very small. There's no integrated anode. The anode is centimeters away in this vacuum system. But we're seeing photon enhancement that's not associated with heat. I'm not going into the details on that, but we have a blue LED that's that's not heating this photon flux into the cathode, and we're getting this very nice demonstration of heat in a microfabricated photocathode. So now the interesting thing is you need the photons, right? It's not going to work in the dark. There are people with photons. This is the solar thermal setup, PS10 in Spain, with all these mirrors directing the light onto this heat engine. So this has no photon enhanced thermionic converter at all. It's either people use Stirling cycles, gas turbine, you know, steam turbine, that kind of thing. And so what the peak converter could do is be attached on top of this and harvest additional energy. If it didn't work, it would be the same as what's there now. It's a topping cycle. So the reject heat is at high enough temperature to get your steam conversion going. So if you do the numbers on this, and this Nature Materials does that, it looks very, very interesting. So maybe it doesn't have to be perfect to be useful, which is nice in the new technology. So if you look at a 12-inch wafer, and if you concentrate light, it's about 15 kilowatts per 12-inch wafer, is what kind of numbers you're looking at. That is, and we're generously assuming $10,000 for that wafer. MEMS people would love to have $10,000 for wafers, but this is an exotic wafer, and it's a stack and all, so that's probably, generous. But so it's 60 cents per watt to install this thing, and if we assume 25% efficiency, which is not rocket, kind of pipe dream, and then you look at the levelized cost of electricity versus the device cost for all these different things. This is different efficiency. When you put this on a solar thermal setup, you end up at 25% with something that's better than a lot of alternatives and getting near supercritical coal. So you would have something that could make a big contribution, we think, in these combined cycle converters. Now, Nick Melosh is completely sold on this photon enhancement. I would like things that work in the dark. And if you had a thermionic converter, it could go on your water heater or your dorm's water heater that would work with a thermoelectric. So you have a thermionic thermoelectric fan that would be quiet, no engine going, and all solid state, and work in this tandem cycle and make electricity while you make hot water. That turns out to be a very attractive proposition, especially with a lot of gas available locally. I don't know if they're drilling or fracking underneath your campus, but anyway, I guess there's a lot of this found around here that might play a role as a bridge. So I am, as usual, running out of time. I guess, what about vacuum, other applications? I guess people think of terahertz and they think of one thing, which is surveillance, imaging, and that kind of thing. And the motivation we have is ultra-wide, not ultra-wide, extreme wideband communication, where you could get significant power at terahertz. And in fact, you need a vacuum electronic device to do that. But and I look at it at the time, I think maybe I've spent too much time on the energy front, and so I will just jump past this. Another retro thing, this was 1920s technology as the inspiration for our 21st century cavity, maybe using deep reactive ion etching, and some clever processing. Justin Snap is the lead student. Lateral thermionic emitters made out of silicon carbide. And so in conclusion, that we're finally getting current out very recently. Conclusion is that I think that there are lots of ways to do vacuum, and maybe we can now think of a vacuum-based microsystems technology that would revisit some applications that were looked at in the previous century. The technology wasn't there to make these practical. So in terms of acknowledgments, I've been at Stanford for 6 years, and I've met wonderful people, some of whom left as soon after I got there, like Tom Kenny, going to DARPA. Tom Lee is now at DARPA. The dean says no more people going to DARPA. Maryland has to, you can drive down here. Okay? It's a disruptive thing for West Coast people to go to DARPA. You get so many frequent flyer miles that the flight attendants know you by first name, leading to Washington from San Francisco. So anyway, Tom has actually moved back, so he's around. If you haven't heard a talk by him, he would be a candidate for a very interesting seminar. So Jens, a very senior guy, came over from Denmark. Piero Pianetta's at SLAC, and Ziek Shen is a guy with an appointment in 3 different departments. I would like to add EE and divide it by 4 ways, but in any case, Roy Mabudian at Berkeley and Sharif Sedki at the American University in Cairo. And the people who are really doing the work, of course, Igor would be the lead on the energy project. Jay Provine is ALD guru. Jay and Sharon and Justin are grad students. And the funding would be, as we were talking about, it's a mixed bag, okay, of various sources that are put together. Nick would have some basic energy sciences funding, partly through SLAC, which is a DOE lab, partly independent, little bits of money here and there. GCEP is a Stanford consortium. Toyota, Exxon, GE, and Schlumberger put in a lot of money 10 years ago for global climate and energy research, kind of way ahead of the curve. The final year or two, we got a GCEP project. We, Jens, and Piero, and we're not pictured for some reason. Anyway, and so Bosch and Honeywell are members of this DARPA Center for Interfacial Engineering, which has been something that's funded this more basic research. So I think where there's a will, there's a way, often to find out a means of doing something that I think would be very important, even though it's, I think, a very long-term research that will take additional major programs. So I would like to have some more major investment from the U.S. Federal government in this area, because I think it has tremendous progress. And if you learn to operate at that high temperature, Europe is interested in doing that for other reasons. You know, I think there's a lot of things we could benefit from being able to do sensing and control in these harsh environments. So with that, I'll wrap it up and appreciate your attention. And thank you.
Okay, any questions for the speaker?
Yes, okay. Well, actually, Ian's emceeing. I'm just
Feel free.
questions.
So you talked a bit about this issue of hotspots in the nanocrystalline diamond
Yes.
films. So this is really a two-part question. Is that true for even very thin diamond layers? And the second part is that true for both p-doped, undoped, or lightly p-doped, heavily p-doped, and even n-type?
Okay, these were fairly thick films. Okay, the assumption is that if you went in with a scanning probe of something, there's instruments that could identify what's going on in these. You know, you get the XY coordinates and you go in and you see, is it a grain boundary? Is it some defect? But they have done all of that and haven't come to a conclusion yet as to what's going on. So it's not very well understood. N-type is the one that's showing a low work function. And so I'm quoting those results. I think it's not very well explored. There aren't that many groups doing diamond. And Nemenich would be one of the leaders, but there's Colin at Vanderbilt and the other people working away on the material side. So Milosh is a diamond guy. He says he's revised his group's papers because his own group, understanding would be evolving as they do more experiments. So he felt stick with the tried and true to do a device on diamond was premature. But I think it's tremendous promise. And if we could use its benefits and use it in an ultra-thin layer, then maybe the backing layer is something that might, we have this challenge of a heterostructure that's going to get very hot. Certainly a lot of intermediate materials challenges, but I think it's a wide open question what's going to happen to what the ultimate cathode in the anode will be. They have to be friendly for your nano center, or they don't really exist for us. We need to develop the technologies to do this at the wafer level in order to be contributing to these solar thermal or water heater cogen kind of projects. Sorry, the literature is not that deep. So, here.
So I'm just wondering about how you do the materials optimization here. In the photon enhanced version, you use a high temperature material because it needs to be stable at high temperature. But does that match to the solar spectrum decently? And then the other question is, so you put a cesium layer on the surface or some low work function thing, so now you have a Schottky barrier somehow in the system?
And actually that can be used to advantage. They're potentially, the way so the question on first, let me answer the question of whether ternary materials that are matched to our sun, silicon carbide would match to some star. I'm I'm sure. We don't want to be there in that spectrum, though. We're fried, right? So the band gap is too high, the wavelength too short. So we went through all of the catalog of materials, and some of the ternary ones are matched rather well. Silicon isn't that bad, okay? It may not have to be perfect. I think we're probably going to find something that's okay. If you read the paper in Nature Materials, Melosh would argue that the peat converter can be efficient at lower temperatures. And that I think there's a big difference between operating at 1500 C and operating at 600 or 700 C. And the photon enhancement allows you to drop the temperature. It may be able to be obtained earlier because of the our vacuum seals, thermal expansion. Everything is going to get worse if we're operating at a really high temperature. But I think silicon may not really be part of the converter. Ultimately, is accepted as a supporting structure, and maybe to aid in the fabrication. And then ultimately, it's gone because it can't take it at the kind of elevated temperature.
And the Schottky barrier?
Oh, the Schottky barrier. Lots of interesting, under lots of illumination. The low work function phenomena would be something that has some aspects to it. The cesium is actually out of the surface a little bit, but it wouldn't be lowering the work function by creating a barrier. And so you, I think we're okay there, or there will be materials that are okay. This is real materials discovery with Norskov. Ab initio, trying to get guidance for our ALD from these cluster computing calculations. We have tried doped graphene as a potential candidate of material, which has some interesting properties. So I think the space is very broad, and our computing is quite limited in terms of the number of atoms in that can be tackled. And so I think there'll be things that are kind of intuitive, where structuring the surface can make a big difference, getting large surface area, using geometric effects to lower work functions. So it's a foray into basic materials development. One of my most extreme forays, because generally you would not discover a particular material stack, but we managed to scrape up some money to go try. So we'll see if we're successful. So,
More questions? So I'll ask a question, since there's a lot of grad students and some postdocs out here.
Okay.
So would you, as they think about research plans or startup companies, would you feel like this energy conversion field is wide open to people like this, or maybe a little bit limited and competitive and a difficult sell?
To go raise money to do this would be something that the third guy, Melosh, would be thinking could happen within the next 2 or 3 years, that it would be enough to get credibility for the venture capitalists to dive in. Having been around the block a few more times than he, and seeing technologies take time to develop, and if it was my money, I'm not a VC, by the way, to be able to invest, but with all of those qualifications and extreme over-conservatism of age, I would say it'll probably be 2018, something before you would know one way or the other. And that's still pretty aggressive, but I think if you got the low work function materials, all this is borrowing MEMS technology, right? And someone said it wasn't MEMS because nothing moved. Okay, but in fact, if we needed it to move, we could steal a few nanowatts to make it move. And that's another thing that was not possible. If there was some regime of operation, I challenged Jay Lee, the grad student, to think of actually a cathode that looks like it's suspended and could be moved, and that might be an operating mode that could be advantageous. Inconceivable for the Russians, doing their conventional machining. But all that's basically free for us as a system. So all of that ISR kind of system know-how is ready at our disposal, and that I think is a game changer. So it would be neat to be able to make that, to see those towers go up. California, of course, has a lot of deserts, but they banned a lot of the solar, thermal solar energy for what it ruins the view. They have these things, small animals. I was so frustrated with our legislature doing this that the poor lizards would be in the shade, underneath some of these things, and they would be having a good life. You can't let them do that. At some point, you go a little over the top, and probably better to have that out in the desert than maybe a nuclear reactor on the beach. Might be a trade-off. So, in any event, I think the solar thermal could be maybe get that extra boost to become something that didn't need any subsidies, and it could just undercut the fossil fuel. And it's not going to. I guess you're working on batteries. You need, I mean, how are you going to store this at night? The Spanish had put molten, salt. I have some way of heating some stuff and putting it in the ground, and then running things at night at a limited level. But I think there's a lot of work to do that would involve nanotechnology across the board. The batteries will be another major challenge. So anyway, I think it'd be nice if some of you got job offers you couldn't refuse, pulling away your first job as your PhDs or masters are coming soon. Any undergrads in the audience?
Oh, yeah.
Okay, there's a hi. So, yeah, completely in talk mode. You were in my office 3 weeks ago, 2 weeks ago, something like that. So anyway, but that was talking about bio, right? That's the other. So I've gone kind of schizophrenic. That's some people do. I have a bio side that's not been talked about, but I can't resist contributing to this side. So I'm being sort of pulled apart by application. So you got two wings of the group. So anyway, but I think the men's industry is going to be growing, and so our Tom Kenny's last student, Violet Hugh, hired by Apple. Working with Pete Hartwell, who used to be at HP Labs, is moving to Apple. Right? Google would be hiring people, and then they go in and they never talk, so we don't know what they're doing in there. They're doing something, and they're not being hired for their software skills, because I guarantee you Violet doesn't have it. I know, signed her thesis, she's brilliant ME, but not someone who's going to write some app, but she might accelerate iPhone 7's use of that. I think that's an exciting development to have men's people on the inside of these mega companies.
Pete is on our strategic advisory council.
Okay. Okay. So anyway, and then you can go into the energy business once that begins to be up. And use the same kinds of designs.
Well,
so if you did this water tower heating and you put the thing around it, how would that compare to just having solar panels?
Well, the solar panel, multi-junction solar cells are wonderful. They don't really work well when they're hot. There would be some major material challenges for both. To put those towers up, the energy flux from the sun is even in the desert is going to, we're estimating 15 kilowatts concentrated on a 12-inch wafer, right? So there's if you're going to do gigawatts, you're going to have a significant infrastructure out there. It won't be in California because we like our deserts the way they are, or maybe we'll change our mind about it. You could put them down in the middle of nowhere. You put them on you have roads somewhere. You can put them down the roads.
you have to have the ones.
And you have to do something at night. California, we pump water uphill using nuclear power. And uphill meaning in the Sierras, up thousands of feet, and then essentially use high mountain lakes as batteries and run it through the turbines in the afternoon. So there's a little bit of interesting things. You have elevation gradients. You can get some benefit because the reactors, we don't use the full load at night. So there's a couple of nuclear reactors in California that are powering significant amount of stuff. So the idea that this would be going full blast on the peak of the hottest day, you're getting maximum energy out, that's kind of a nice boost. Google's green energy czar, who felt it was not going to help their servers in the near term, right? It's too far out. But they would be investing in, they certainly have money, and they're certainly interested in dealing with the part political, the part the financial problem of paying for the massive amount of energy their servers are needing. So in the West, there are hydro dams in the Pacific Northwest. They have giant servers. If you go on Google, you can see these huge installations with very inexpensive power right next to the dam. They used to put aluminum smelters up in the Pacific Northwest because of cheap power. Now it's Facebook. Server farms is what would be driving that. So anyway, I would hope that we can nucleate something that would drive some materials research and some MEMS. This is MEMS. I think it is.
This is system.
Yeah.
Any last questions?
So if anyone wants to come up,
Yeah.
feel free to.
Yeah, Professor Howe is going to stick around for a
Yeah,
while,
I
so
know.
especially prospective postdoctoral associates.
Yeah.
Please come up front and talk.
And let's thank him one more time.